Welcome to the High Performance HVAC podcast. I am one of your hosts, Adam Mufich with National Comfort Institute, and I am joined today with my co-host.
Hey guys, this is Casey with NCI, and we've got a awesome guest with us today. We got Ty. What's going on,
Hello,
Ty?
everybody. Oh, it's just another beautiful day in the neighborhood.
Oh yeah, you know it is. So where are you at in the world today?
Right now, I'm in Carlsbad, Texas.
Nice.
Yep, and we had some really big developments. We recently got a Dollar General store, so we can get milk and some drinks without having to go all the way into town. So, we're super excited about that.
That's always beneficial. I like
Yeah.
those Dollar Generals.
Yeah, it's really hard to find them, but if you look close, you can see one here or there.
Oh yeah.
I saw somebody posted a picture from Mars online that looked like a door, like a cave door. And somebody made a response with shuffling your hands back and forth like the Dollar General guys looking to move in and take over. But yeah, anyway, sorry.
My biggest issue with Mars is that the capacitors always leak. So I switched over to AMRAD.
That's good. Is AMRAD the only no, Mars is also the US made now, is it not?
I don't know. I only know of Titan HD, not just Titan, but Titan HD, and then I know AMRAD, which is right in Florida, which is just amazing capacitors. I'm not sponsored to say nothing. It's just, you want a good capacitor, that's it. It's just, I just gave up with everything else and just started using them. And they make singles. You don't have to get everyone's like, oh, I don't need that big. No, they make individual capacitors. And they make individual capacitors with the the compressor protection terminal, CPT terminal. So you can hook, if you have a start kit, you can hook it up to that terminal. And if your capacitor blows or fails, it won't keep that start kit constantly just slamming that start windings of the compressor. So, I mean, yeah, AMRAD all the way. AMRAD singles, AMRAD dual runs, or you can use the big multi-AMRADs, but yeah, made in Florida. You can go visit the factory. You can see the people that make them right here in the United States of Americana.
Nice. I wonder where you probably pick those up on supplyhouse.com or something like that. My biggest problem with capacitors is like when you go to a supply house, they usually only have one or two brands, usually one brand, and it's usually a brand that I don't want to use, right?
Yeah.
Right. So I used to hardcore on buying locally, buying from my local supply houses. But you know, we've gotten where the supply houses stopped working with us. They stopped growing. So I need this capacitor in, and luckily my local one does carry AMRAD, so that's cool. But when I need other parts in, like, oh, sorry, we don't have that. Or I need a part, and like, oh, well, we'll order it, and it'll be a few weeks to get here. So I go online and order it from an online supply house, and I can have it here like the next day or 2 days. And if it's after 5, oh, we shut the doors at 5. Well, my job doesn't stop at 5. Like, I still need parts. And so it's just really frustrating to me if I have to gather and have my own supply house, or I have to order stuff myself. It really limits me at my need for my local wholesaler. And I want to support my local wholesaler, but I think we're getting to where wholesalers are not growing with the needs of the HVAC contractors. But that's just my feelings, and it doesn't really matter because I can't change nothing. But yeah, online is where I've been getting a lot of my stuff.
You know, one thing I also noticed about the local distributors and wholesalers and that is they don't have that was always the go-to place for HVAC tools, right? When you were sitting there waiting, you'd look at the wall of tools and you'd pick things up and like, what's this? This is pretty cool. And they would always have really cool things. And now it seems like it's super limited. Either that or we're exposed to this new, online thing where you see all these different videos of the cool tools coming out and they just don't have it all, not everything's available.
Yeah, that may be some of the change, but also we get slammed with customers all the time. I mean, the customers are a lot of customers are they're mad. I mean, they're mean. Anybody dealing with anything in customer service, it's challenging. So when I go to the supply house and now I'm going to buy something from them, I don't want them treating me like trash. I don't want them making fun of me or like I'm in their way or I'm, ruining their day, asking for a part or a warranty. It's like, hey, how about you guys learn some customer service too? I have to learn customer service and deal with customers that I don't like, and I still put a smile on my face. They never know I don't like them. How about you give me a little bit of respect you, Mr. Supply House guy, who's working in this nice air-conditioned building and doesn't have to go crawl on top of a roof or in an attic at a 100-degree day. Like, I'm sure your job is stressful. I couldn't do your job because there's too many numbers, but give me a little bit of respect, right? It's like the donuts aren't enough.
Oh, you get donuts by you?
Oh, yeah, that's like the whole reason I used to go to Supply House in the morning was like, hey, grab some donuts. But then I started gaining weight and I realized that's a bad idea.
Nice. So, hey, Ty, I just watched a series of videos that you put out recently, and I thought they were really cool. I was like kind of hooked on it, and they were about vacuum. You pulled a vacuum on a vacuum chamber, and you put water droplets on different materials. You want to talk a little bit about that? What you were trying to accomplish with that?
I don't know. It might suck.
Bada bum.
It's actually pressure differential. The vacuum pump is just creating a pressure differential. It's just simply moving air or molecules from one side to the other, and by dropping the pressure, it makes a pressure differential. And your vacuum cleaner, it's actually quite interesting. Your vacuum cleaner is simply doing that same thing. It's making a pressure differential, and so the air pressure, the atmospheric pressure on the outside of the vacuum is greater than the inside. So the air moves from the outside higher pressure to the lower pressure inside. And the vacuum cleaner specifically needs to go in a very small area, like a small clearance, and you have the brushes making turbulence. And as the velocity, you guys talk about airflow, as the velocity of the air travels through at such a fast rate of speed, it also picks up the dirt and dust, and it's able to carry it into the bag. And then, of course, the bag has a filter, which is also important in displacement and goes right back to the air. So it's a lot of air conditioning goes into a vacuum cleaner. We're talking specifically about a vacuum pump. Same thing applies. We just need to go to a deeper level. So you want to go to that deeper level? Is that what you're saying?
Oh, yeah. Let's get deep.
Okay. All right. So it's cool how the vacuum pump works. The very first ones were actually that we used in the field were refrigerator compressors. That was the vacuum pump. And it was a serviceable one where you could take it apart, you could change the oil, but you couldn't pull very deep with those. It was just pistons and rings. So your vacuum was less than atmospheric pressure. It did help boil some of the water and it helped move air, but it couldn't get down low enough to the deep microns to really boil the water away. And so that's when the triple nitrogen really come in handy, because you could add nitrogen through, pull the vacuum, add nitrogen, and it just helped displace and sweep some of that, what you couldn't get out. And we had mineral oil. I mean, how cool is mineral oil? It's like, it's the tank of oil, right? So you didn't have to worry about, you got some moisture in there. It wasn't good for it, but it would handle it. It was, you get some oxidation. It didn't care. It left it there. It was an awesome oil. And now we have, POE oil, it works great, but it's very sensitive. And I've had some employees like this. They were great employees. They were awesome, but you had to treat them a little different. They were a little bit more sensitive. You had to be careful while you're introduced to them and how you talk to them. And they worked good and made you money. You just had to understand that. And so that's been a huge difference. But then later we came out with the belt drive vacuum pumps, but they were the kind with the, oh my gosh, I can't remember the word, the vanes, and they would spin. And the oil makes the seal, and that's what's able to really drop that vacuum level down. Of course, if you have dirty vacuum pump oil, the size of the molecules of water is greater than the size of the oil in the vacuum pump. And so when your vacuum pump gets dirty, you can't pull as down of a deep of a micron. So, making sure we had the right oil, but now we're able to get down into deep microns. We're able to actually boil the water away. I have a Carrier book from 74, I think, and it talks about pulling in a deep vacuum. And today, kids are like, oh, this vacuum stuff's new. And it's not new. It's not new at all. Let's see. Hang on 1 minute. Let me have to cut this out. I have a vacuum. Here we go. Nope, not that one. I got all kinds of toys. So this is my first micron gauge, right? They're not new. It's quite old. You had the temperature calibrated. Wow. And so we actually were able to measure microns back in the day because it was important. The review of a vacuum for the service engineers goes back to 1950s. So doing proper vacuum, using big hoses and using good oil and the proper vacuum pump and all this testing goes way back in the 50s. It's not new. Saying, if you pull a vacuum too fast, it's going to freeze the water. That's not old school. That's no school. There's actually an effect. There's a true term saying, I can't remember the name of the scientific term, but if you put out false information fast enough, it takes more time using the truth to uncover it. And by that time, they go on the new false information. There's also another term saying the first way you hear something is the way you're most likely to believe it. So when you have something like pull the vacuum too fast, you're going to freeze the water, that combined with people just keep saying it over and over and over, people just like, oh, it's got to be true because I've heard it that way my whole life. And now you want to change what somebody's believed their whole life. They've been told this, they've repeated this, and now you're going to challenge somebody saying something different. It doesn't matter how much science or math you show them. It's very difficult for somebody to accept that. And so that's what these experiments are about, is making it visual, right? We have the review of vacuum for the service engineers. It has all the science, the math, the formulas, the charts, but it's just numbers. How can we make it where we can see it? And so that's what I like to do. I want to see it. Show me the science, because nobody's ever showed me the money. Show me the science. And so that's what I want to do, is show the science. So all of this stuff about vacuum is really about making that invisible visible. That's my goal.
Yeah, so that book, there was one or two sentences that really stuck out on that review of vacuum for service engineers that I thought was incredible. That really pushed me over the edge. And like you said, it was from what, the 50s, 1950s or something like that.
Yep.
But it said something, and I'm not going to quote it because I have no clue exactly what it says. But basically, what it says is, don't waste your time pulling vacuums with quarter-inch hoses ever. It takes way too much time and labor, so it's a waste of time. Don't do it, period. And
yes,
that's what it said. You know what I mean? So there's people that will argue to death that it's okay. I do it all the time, and just because you do it all the time doesn't mean it's right. And you're actually, are you doing a good job, right?
And now let's address that, because a reasonable person can look at that and be like, I don't see the difference because I've never done it, right? That's a valid concern because they've only done it one way. So they haven't done it any other ways. That's a valid concern. And what's the other one you hear about using bigger hoses? I'm sure you've heard it. Why use a bigger hose? Because
if you use a bigger, the inlet of the hose, the actual part that you screw on, is too small. It's smaller than the hose itself, right? The restriction, the pressure drop.
And it's reasonable for somebody to see, well, that hole is a quarter inch. So what does it matter if I use a bigger hole or a bigger hose if that hole is only a quarter inch? And it's a valid concern. So what I suggest people to do is go to the hardware store and buy 2 water hoses the same length, but buy one, the smallest one you can possibly buy, and buy one that's the biggest one you could possibly buy. All right, so same length, different diameter hoses. And then when you get home, get yourself a bucket and a stopwatch, and look inside of your spigot. Not a ball valve, but the old-fashioned screw-hole spigot. When you open that up all the way, well, don't look at it while you're opening it up. Actually do that, but record it, because that'll be funny. But if you look at when that's completely opened up, the hole is very, very, very small. It's a little bitty hole. It's very, very tiny. And so that's all the flow you're going to get. But if you hook that big hose to it and measure it in a bucket, that bucket fills up really, really fast. And if you put the little bitty hose on there, the bucket doesn't fill up as fast, but you have that same size hole. So that's a way that we can see it. We can actually see what's happening, that, hey, even in water, something we work with every day, even though it's going to that same size hole, the water itself in a bigger pipe, there's less restriction. So in short, that little hole, a temporary restriction, versus the entire length of the hole being a permanent restriction and a permanent pressure drop. That's kind of the relation to it. But when you go into vacuum, you get to a whole nother level. It's like onions. It's got layers. So when you get to vacuum conductance, it actually talks about, as the vacuum gets lower and lower pressure, how that bigger hose is even more important. And there's a bunch of math and science that goes in there. But it's really cool. And then if you've only tried it through the manifold, through the small hoses, and then you actually try it with the bigger hoses, then you get to see with your own experience, wow, this really is faster. Because I thought the same thing. It was back 15 years ago. The guy's name was David Boyd. He started pushing bigger hoses, changing the vacuum pump oil, removing valve cores. 15 years ago, to me, it was new. I was like, well, he introduced me to the book, Review of Vacuum for the Service Engineer. And I'm like, I got my doubts. I'm skeptical. I have my concerns, like a president. Anyway, so what I do is, like, I tried it. I got the stuff. I hooked it up. I tried it. And it's like, it does work. Like, that is so cool. So I started doing more and more stuff and realized, wow, the guy really knows what he's talking about. So doing it, if you've only done it one way, cool. Try doing it another way. And then here's some things like with the water hose, you can try it yourself and then get the book and you can see all the science and math behind it.
Yeah, that's it is funny because I remember the first time, and I'll be completely honest, I haven't been pulling a vacuum the correct way and using larger hoses for that many years. But I think I bought the Appian, what are they called, like the Mega Flow kit or whatever, when that
Yep,
first came out, and
I
I was
got one
like,
right back there.
I'll see how this is gonna go. And like the first time I pulled the vacuum. And I saw within like a minute, I'm under 500 microns. I'm like, what the heck just happened? You know? And it's amazing because I remember like my first micron gauge was years ago and I had the Subco micron gauge. You remember the ones with the little lights?
I had one.
Those are, well, I'm not going to say if they're, yeah, we'll pass on that. But yeah.
Skip.
But I always thought it was broken, and it might have been broken. But yeah, I had a difficult time trying to pull a vacuum.
I sold mine to a friend, and he prefers that one because he says he can get to a deeper micron faster with that micron gauge than another one.
Huh. Okay.
So if he uses that one, it'll show a deeper vacuum faster than his other accurate micron gauges. It's like, do you want the light that says, hey, you did a good job, or do you want to actually know that you did a good job?
Yeah.
So what was the problem we had back then when we had to use micron gauges and people would say the same, this one thing you'd always hear: I can't use a micron gauge, it's going to take too long. I'll never get the job done. I got to get home. That's what you heard all the time. So people weren't using micron gauges because it would take too long. So then enter large vacuum hoses, which is just reintroducing information. It's not new. We go back to using larger hoses. Before we used copper. It was large copper lines and flare fittings. And so now we have the black hoses, which makes it easy. So now we're able to then pull a deep vacuum and do it in a short amount of time. So we have the win of both worlds, which then rolled in a new concept. What's the new thing after you hear from that?
As far as the big hoses, big pumps, right? Big pumps, big hoses. No, I'm missing it.
We'll get to the pumps here in a little bit, but before it was like, hey, I can't pull a deep vac with microns because I don't have that much time to do it. Cool. Big hoses. So we introduced big hoses and the micron gauge. And then we pull the cords, for sure makes a difference. But then you hear, oh, no, now you can't pull the vacuum too fast because you'll freeze the water. So like, then all of a sudden people wanted a slow vacuum again. And it's like, to me, it's just an excuse to not try another way. And it sounds good. Oh, if you pull a vacuum too fast, it freezes. And I did research where that came from. My science experiment was trying to prove that that's true or false. But I went back to find out where did that start from. And I found 3 start locations. One is when we started doing service work and we actually had good deep vacuum pumps. They would be working on a unit and then they would pull a vacuum. And as you're pulling a vacuum very quickly, when you're working in a refrigeration system, you have a leak. All the refrigerant's out, you have zero pressure. You have zero pressure in your system. Are you going to hook your recovery machine up to that?
No.
No, of course not, right? It's zero pressure. EPA even says that's okay. It's zero pressure. Is all the refrigerant out of that system, though?
No.
No, absolutely not. There's refrigerant in there because when we pull a vacuum, then we add 14.7 psi just to get to 0 psi equal with the atmospheric pressure. And then the oil also absorbs a lot of that refrigerant. I can tell you that for the first time that I pumped the unit down and I thought, oh, I don't need to shut the suction valve off and it bounces in the truck and sprays out the back. Yeah, there's refrigerant in the oil. So when they first started using these vacuum pumps, they were a lot more powerful and faster. It was pulling the oil out of the compressor crankcase and it started to freeze as the refrigerant was changing state from liquid to vapor, boiling out of the oil, dropped the temperature of the oil, and the crankcase of the compressor would freeze. So what was people thinking? Oh, well, if we pull a vacuum fast, it's freezing because that's what they saw. That was their experience. Second thing was when people used vacuum chambers, started using vacuum chambers and testing stuff, and they had a glass vacuum chamber or a glass jar inside of the vacuum chamber, and they had water on it, and it started boiling it away. That water Latent heat changes state from a liquid to a vapor. And anytime any substance changes state from a liquid to vapor, it absorbs heat. It's latent heat. This is 1 pound of water, approximately. To boil this from 212 liquid to 212 vapor is 970 BTUs of latent heat. To go from 32 to 212 is only 180 BTUs. So if I poured this on you at 32 degrees, how would you feel, Adam? Liquid, but 32 degrees, how would you feel?
Very cold.
Yeah. Now, if I was to heat this up to 212, still liquid, and pour it on you, how would you feel?
Hot and bothered. Yeah.
Yeah. Yes, exactly. So would you agree that 180 BTUs is kind of a big deal?
Yeah.
I would. That's huge.
Yeah.
Compared to 970 if this was to evaporate or boil, change state from liquid to vapor. It's a lot of BTU. So if I have this in the vacuum chamber and then I hook a vacuum pump to it, I'm boiling that water off the top because we've reduced the atmospheric pressure, keeping it liquid. We remove the atmospheric pressure. It's changing state from liquid to vapor. It's absorbing heat. Well, a vacuum chamber doesn't have air around it. It's nothing. It's an insulator. So as we start boiling this water off from a liquid to vapor, it's absorbing heat. What is it absorbing heat away from?
Itself.
Itself, yes. It's boiling the heat away from itself. So what's the temperature of the water doing?
It's dropping. Yeah.
It's dropping, exactly right. So we're going from whatever temperature we put it in, and sensible heat's easy to change, all the way down to 32. And then all of this gets to be 32, but we're still boiling water out. What's going to be happening?
You're going to start freezing once you hit 32,
yes!
Right?
Absolutely right. So it's latent heat. It takes 144 BTU to make it change state from a liquid to a solid. So as some of that water is boiling, it's still absorbing heat. It's taking the heat from it being liquid and making it turn into a solid. So it's making it change state. So if you do that in a vacuum chamber, you start to see the water freeze. And so you're like, oh, well, if we pull the vacuum too fast, it's going to freeze. And then in 1993, it ended up in the EPA test. If you pull the vacuum too fast, it's going to freeze. And so that's kind of like where that came from. But what we've left out is thermodynamics. We're going to take the refrigerant aspect out of it. I'd actually go back to the refrigerant aspect about it. We know that we have liquid refrigerant inside of an evaporator coil, and we lower the pressure, we lower the
temperature,
we lower the boiling point. Exactly. So in that evaporator coil, it's under atmospheric or perfect test conditions. We have a 4-degree evaporator, which isn't a standard. It's just in a book. We're going to go with it. By lowering the pressure, I lower that boiling point to where it's boiling at 40 degrees Fahrenheit. The refrigerant's violently boiling at 40 degrees Fahrenheit. We all agree with that, right? It's latent heat. Now, I can have a little bit of refrigerant in there boiling from liquid to vapor, or I can have a whole lot of liquid boiling from a liquid to vapor, but it's still going to be at its 40 degrees. Now, what we all forget about in school was that liquid line coming into that metering device. It's a subcooled into that metering device. It's a subcooled liquid. That's right. Yeah. And then coming out of the metering device, we have a pressure drop. What's the state of refrigerant on the other side of that metering device?
It's a mixture of liquid and vapor, right?
Yes, it is a mixture of liquid and vapor. We went in as a subcooled liquid. Coming out, there's liquid and there's vapor together. So what happened through that metering device? Why is there now a mixture?
The sudden pressure drop across the metering device causes the liquid refrigerant to instantly, some of it flash off into vapor.
Yes.
Right? And you still have some remaining liquid.
Absolutely right.
I feel like this is like a test in school. I'm like waiting to give you the wrong answer for something.
But if you're thinking about that, other people are thinking about it too. I'm not putting you on the spot because we don't go through this. We don't answer these questions every day in the field. It's not like, oh, well, I'm going to go consider what my adiabatic expansion is. No, it's in school theory stuff. So for us, don't feel bad. Nobody doesn't know these answers. It's been a while since we've talked about it. But that's why it's important for us to revisit these fundamentals. So that refrigerant comes in at 100 degrees, and then it's coming out, say, 45, 43 degrees. What happened between that liquid 100 degrees and now we had to drop it? Just because we dropped pressure, we can drop temperature, but that's not enough. I have to physically drop the temperature of this liquid refrigerant. For me to do that, I need refrigeration. I'm going to sacrifice, and this is just lab conditions. This number is not standard, But if I sacrifice 25% of this liquid, I sacrifice it, I gave it up, dropping the pressure, this 25%, bam, instantly flashes, immediately changes state from a liquid to a vapor. If it was water, it'd be 970 BTUs for every 1 pound that changed state. So if I sacrifice 25% of this liquid, I can drop the remaining liquid into its saturation temperature, 43, 45, 40, whatever we're going to be to the atmospheric conditions. So coming to the metering device, yes, we have a pressure drop. Yes, we have a temperature drop, but we have to sacrifice some of that liquid refrigerant to drop the remaining liquid down so that we can have it at saturation. So this is why in commercial refrigeration, you'll see subcoolers that try to cool that subcool that liquid even more when it comes into the metering device, so they don't lose as much flash gas. So the less flash gas they have, then the more liquid refrigerant we still have to change state. So what that means in our vacuum chamber, same thing. If I pull a vacuum, as this refrigerant's boiling off, it's changing state from liquid to vapor. But as it's changing state to a vapor, that vapor pressure is also applying on it, keeping it from pulling as fast. So the bigger the vacuum pump, then the less vapor pressure I have, and the faster I can make that water boil. And if I have enough water, I can boil this from a liquid to vapor and then have enough to not only cool, but freeze what's left over. And that's science. Yes, big, giant vacuum pump, vacuum chamber, I can absolutely make this freeze. Can't happen. What are we missing in this equation from a vacuum chamber?
We're not pulling a vacuum on copper lines in a vacuum chamber, right? Like, so you have
Absolutely.
the thermal conductivity of the copper.
Yes, absolutely right. It's like our whole entire HVAC system. It's almost like it's made to transfer heat. It's like it's made to take heat from one area to another. It's like our evaporator coils or heat exchangers made to move heat from outside to inside, and our outside's made to move heat from inside to the cool air outside. It's like our whole system, like a 5-ton unit, is made to move 5 tons of cooling capacity. Like, what? Isn't that amazing? So the whole system's made for heat transfer. So because we have copper lines, and as long as they're hot or warm, we are boiling this water from a liquid to a vapor. We don't only have to get this to freeze, what it's sticking to has to also be able to maintain ice. So if you take an ice cube and you go stick it on a piece of 100-degree copper, what's the ice going to do?
It's going to melt, become water.
It's going to melt. Exactly right. It's like physics. Thermodynamics play a part. Yes, it will melt. So in the summertime, if you say you're going to pull a vacuum too fast, it's going to freeze, then you have to be able to take an ice cube, put it on a piece of copper, and convince me that ice cube is not going to melt. Right? So, it's not going to happen. Or put it in an evaporator coil in the summer. Put the ice cube in that coil and see what happens. It melts. So, yes, we do have microscopic moisture that gets trapped on the sidewalls of the copper. Yes, it takes time to boil that out. It takes a little bit of a very deep vacuum to make sure we boil all that little bit of water out. But also, it's not going to turn to this ice crystal and just magically be an ice crystal touching copper that's anywhere from 70 to 100 and something degrees, depending on what day it is. It's not going to happen. Once we get below 40, I think that's still high, but 40 is a safe number to say, hey, it's unlikely we're going to have ice crystals on 40-degree copper. And even if we had enough liquid water to change state from liquid to vapor and cool the copper and make the copper freeze and also maintain that, that's a lot of science. So I did an experiment. I did some calculations. I did some math. And if we took a 70-degree day at 85% relative humidity, actually I have the number somewhere, 85% relative humidity, and I had 15-foot line sets, 3/4 ACR suction line, 3/8 ACR liquid line, and I got the grams. And again, it'll drive me crazy. It's here somewhere. It took the grams of water that was in that. It came out to be 1 drop of water, essentially 1 drop of water on a humid, cool day.
Hold on. So are you saying if the entire copper line set was filled with the outside air?
Yes.
Okay, so that's how much water would be inside of the lines if it was completely filled with outside air.
Yes, I did the math. I didn't expect to talk about this, but I did the math on it, and it came down to I got the precise amount of grams of water, and it's 1 drop of water. 1 drop, which is a lot. That's a lot of water. It's more than our filter dryer can handle. It's plus, there's water trap. It's a lot of water, but for us, it's 1 drop of water. If we dehydrate, not including the evaporator coil, the condensing coil, just the line set, one drop of water. So you got to convince me that there's enough BTU in that 1 drop of water to freeze an entire line set.
So you said like the safe temperature outside is 40 degrees, and I thought that was interesting.
70.
So,
Oh yeah, 40. Yeah, sorry.
40 degrees if you're
right.
pulling a vacuum. So like you're ensuring you're not gonna freeze the water, right? But like, and you just said 1 drop of water for a warm day with high humidity outside. So I'm starting to think now, like, all right, so if we're replacing a condenser or a heat pump when it's super cold outside, like I'm thinking about 2 different numbers. Okay, so let's say you cut open the lines and you didn't cap them immediately, right?
Okay.
So if it's 10 degrees outside, what is likely the relative humidity outside?
I don't know, but you're going to have ice.
What do you mean you're going to have ice? Outside?
Outside, why is the humidity outside when it's really cold outside? And we're using cold as a relative term, right? Because cold is actually 0 degrees Kelvin, 0 degrees Rankine, minus 273 Celsius, and minus 460 degrees Fahrenheit. Everything above that is heat. But if we're at, what do you say, 10 degrees?
Yeah.
What is your typical, I like to live in a warmer climate. What's your typical humidity on a 10-degree day?
Very low.
Very low. Why is your humidity so low?
Because air at lower temperatures, the colder it is, the less ability it has to hold water vapor.
Yes. And also with the temperature, a lot of it turns into a crystal, and that crystal is stuck on components. Just like there's invisible water touching all of these surfaces right now, you still have the same thing, but it'll be ice. It'll be a frozen invisible water touching everything. And where you're from, it gets so less heated, so cold that the ice actually comes out of the sky in a frozen state. Like, it's amazing. And then you guys have so much of it, you have to shovel it. It's crazy. Why would you live there? I don't know. But yeah, it's already moisture. So if you had a line set that was open in the winter, the same moisture's there, but it's going to be frozen. It's already going to be frozen because you're already below 32. So that same invisible moisture content is still going to be there, but you have it also in a solid ice form. So it's already frozen. You didn't even pull the vacuum and you already have frozen ice in there in that scenario.
But I'm just wondering, like, okay, so if you said at that higher temperature and higher humidity is 1 drop of water, so how much would it be at that low of temperature and low amount of humidity? Right? It's got to be a lot less. But then I also think, okay, well, you have another guy inside the house that's cutting the line set and removing the evaporator coil. And that inside of the house is probably roughly around 70 degrees. And who knows what the humidity is? Most houses near us in the wintertime is somewhere between 30 to 40%, give or take. But then, like, I think about that, like, what is that? And you always know that humidity moves from a higher concentration to a lower concentration. So it's going to want to migrate into the line set, right?
That's right. It will. And so you have several factors. What's the temperature of the outside versus temperature inside? How long is that line set? How much time do we have to change that temperature? Let me just do some quick math and see if I can find out what that would be. Continue on. Let me just do this math real quick.
Yeah, no, I've thought of it different ways. And actually we had this conversation, Casey and I both had this conversation on a podcast at AHR with Roman and Chris Hughes. Mm-hmm. And we talked about, having to warm up the outdoor unit and line set in order to pull a good vacuum. And Eric Kaiser, a friend of ours from True Tech Tools, he kind of stepped in. He's like, well, the copper is transferring heat from inside the house. And so I'm questioning that too. And I'm sure there's a way to figure out, like, even if you are pulling a vacuum, if the temperature in the house is 70 degrees, how much of those, how many BTUs are being transferred through the wall of that copper to help aid of, assist with the vacuum? And then I also thought about if you have a dual fuel setup or you have a gas furnace and you ran the heat. So now you're transferring how many more BTUs of heat because you're raising that temperature of the evaporator coil that is also transferring into that copper. So I don't know.
So doing the math, this doesn't include what's and this is why it's tricky, right? Because we haven't taken account the outside and the inside. There's a lot of math going on. But if we simplified it and say, hey, let's use a 15-foot line set, 3/4 ACR copper, 3/8 ACR copper, and your condition 10-degree temperature at 10% relative humidity, in the air alone, there would be 0.17 milligrams of water. What that doesn't include is the water that's frozen on the parts of the line set. So it's a very small amount of water that's actually in the air, but what it doesn't calculate is what's actually ice crystals, what has condensed and frozen on the metal line set inside. So it's going to be significantly more than that, but still, I don't know how to calculate that. But it's a small amount of water that's in the air itself. So you're like your point, if we have it warm outside, the heat's going to start moving from the inside to the outside. What's the temperature of that going to be? Well, I don't know, but we do know there's going to be a point to where the outdoor temperature is going to be a lower and the indoor is going to be close to the indoor temperature. And at some point, they're going to, the line going in is going to be warming up and the line coming from outside is going to start cooling off. And so it's just going to be the capacity that copper has to be able to transfer heat. The longer that line set is, the bigger the temperature drop you're going to have. All we need is for one part of that copper to be below freezing, and you're going to have ice. So even if it was only 1 foot of copper that was below 32, then you're going to have ice in that one section. So what's the solution? How do we solve that? Do we wait till spring? Ideally, we could just come back in spring and do all of our service work when it's above 70. That would be perfect. Can we do that?
I mean, in a perfect world, you could do that, but I don't know, like, how homeowners would, if you'd be like, all right, well, I'll do half of the job now and I'll do the other half 6 months from now or whatever,
I mean, I strongly believe we shouldn't have any HVACR equipment in an unconditioned attic. And I strongly believe that we shouldn't have any ductwork in an unconditioned attic for most scenarios. I strongly believe that, but I'm not going to demand that everybody do that because it's better. It's just not reality, right? It's not what we have to work with. So I would love for us to be like, hey, we're only going to work on systems outside when it's above 70. Hey, awesome. I would love heat pumps, right? I mean, even more, it'd just be great. You can, hey, 70 degree, we're going to go work on it. Also, while we're passing these same rules, let's not go in an attic when it's above 80. Cool. Awesome. Even better. All of our work is going to be between spring and fall. Like, I'm loving this. This is great. It would be great. I agree. The problem is we have to get stuff done. We have to still be able to pull vacuums in those conditions. Walk-in freezers, walk-in coolers. We can't be like, oh, we're going to have to take all this food out, put it in a temporary thing so that I can heat this whole entire box up so that I can pull. No, it's like I don't have that luxury. I would love to do that. I can't. I have to get this job done. How can I pull a vacuum when the conditions are not ideal? I need to add something. What can I add?
Heat.
Yes. And we're not talking about basketball, but we do need to bring the heat. We need to add heat to it. So if we heat the lines up to where they're above 40 degrees Fahrenheit or 50 or as warm as we can get them, then if I had heat to water, will water boil faster? Yes. So if I'm pulling into a vacuum, cool, add heat and it will boil faster. Even in the summer, you add heat, the water will boil faster. So the solution in my mind is let's add heat. Now, it's easier said than done. It's not like it's just going to be a snap of the fingers. Most of the time, we can pump the refrigerant down in a condensing unit. Inside, we can run the air handler. Just running the fan moves enough air across that evaporator cool. We add enough heat. If we have a gas furnace, hey, we can actually have the fire in a controlled manner inside some heat exchanger tubes, and we can add heat to the evaporator coil. If it's dual fuel, we can heat that line up. If it's a heat pump without dual fuel, I can put an electric heater underneath that evaporator coil with the fan off, and that heat is going to heat up that evaporator coil. So that's cool. Outside, if it's just that short piece of line set, I have this thing called a heat gun, and I can plug it in and take electricity and convert it into electrical heat, and I can add heat to those line sets and get those line sets plenty warm. And in a vacuum with that hot heat from that heat gun, I'm going to boil that water away. If I have to work on the outside unit, I can energize the crankcase heater. I can use a tank heater. I remember the first time I used one, a guy told me, it's like, hey, you need to charge unit, use a tank heater. And I said, man, thank you very much. This makes it so much faster. We can wrap that around the compressor. We heat it up. We can do what we're not supposed to use and use a torch in the compressor to heat it up. I Do not recommend that. I have done that. But yeah, we heat the oil up. We heat the compressor up. But what about the coils? Well, I keep an ice fishing tent. They're cheap now. It pops up quick. It has insulation. I drop that over the unit. I put my little buddy heater in there, and I have my personal CO monitor with me, so I know I'm not going to, unalive myself from carbon monoxide. But we heat that whole entire tent up. I get that copper, everything above 40 degrees. And now we don't have to worry about the water freezing. The hardest part is going to be the line set if it's across an attic or under a house. That's the hardest thing. Now we're talking about electric heat tape, heat guns, electric heaters, infrared heat lamps. It's a lot more complicated when the line set's running through a very cold climate. But the solution is add heat, or we can come back in the spring.
So I have a really crazy idea and thought that I want to run past you on the line set. And this is probably a bad idea, but I want to throw this out there. Have you ever seen, like, for plumbing, the pipe thawing machines?
No, I haven't.
It's just like basically two big clamps that you clamp onto a metal pipe that has ice frozen inside of it, and it sends electricity through the pipe from one clamp to the other, and it warms up the pipe. Yeah.
What? Yeah, there we go. Why have I not? See, this is things I don't learn by living in a hot climate. That's awesome. Let's try that.
Yeah,
we need to get you.
I would.
You're already in a cold climate.
I'd be worried about maybe doing that with a system, which I don't know how it would react depending on, would it do anything to hurt any of the controls or the compressor on a system? Probably not. It's taking the path of least resistance, right? So it's actually just running from one clamp to the other.
You have an AC unit, right?
Yeah.
Well, let's try it on yours. We'll pump it down,
That's good.
And we'll hook it up. We'll wait till a cold day, pump it down, hook it up, and see if it fries anything.
Yeah.
You have warranty on yours. You're still under warranty. You'll be good. You know how to fix it, so let's try it.
I only have 5 kW backup, so it's not really backup heat. It's it just bumps me up there. Yeah, auxiliary, exactly. So I'd be in a bad situation if it didn't work.
See, I didn't know that existed. See, those are kinds of. That's what HVAC is. We have problems, we have solutions, right? And so, okay, if our problem is we're going to have ice below a temperature, then let's find a solution for it. And just like you came up with this pipe machine, I don't know if it'll work or not, but I'm excited to try it on somebody else's unit. Like, let's try it.
At somebody else's house, right? That's awesome. Very cool. So I have another question for you, science, because you're big on like all the fundamentals in science and that. And I've been thinking about this for a little bit. Casey, I want to ask you, have you ever thought about how a clothes dryer works?
No.
You've never thought about it?
No.
So like recently our dryer, and it's not, I don't know. I think they make appliances to break now, like planned obsolescence. Yes. And I feel 100%. Like it's like every 2 months I'm taking apart my dryer to work on it. And I don't know if I'm doing a bad job of fixing it or if it's just like kind of a piece of junk. It was expensive when I bought it. But I guess like for the longest time, I always thought like a clothes dryer. And I know this doesn't sound like it's related to HVAC, but give me a minute. Right. I always thought like you're heating up your clothes, so you're kind of like baking them dry. But then I started thinking about like what is actually happening. Correct me if I'm wrong. We're just warming up the air around the clothes, giving it a higher potential to hold humidity. So the humidity transfers from a higher source to a lower source. Psychrometrics, right? And then it just exhausts that humid air.
That is exactly what's happening. 100%. And when I teach psychometrics, that's one thing I talk about is a clothes dryer. People say, "Oh, a gas furnace is going to heat it's going to dry the air out." No, it's the fact that if we heat air at all, if we heat the air up, it's like a sponge. If I have a sponge that's squeezed to a certain point, I can only fit so much water into it. But if I let go of the sponge, then all of a sudden it can hold more water. There's the same amount of water in the sponge, but it can hold more. So the clothes dryer is simply allowing the sponge, which is air, to expand, and then it can then hold more water. So if I'm tumbling these wet clothes and I'm moving this air across it that is expanded and warm and has a bigger capacity to hold water, then the water will evaporate, change state from a liquid to a vapor out of the clothes, and then the air is now full of moisture. Oh, I got to do something with it. Let's dump it outside. So we just dump the air outside, and we bring some more air in, and we heat that air up. And yeah, it's entirely psychrometrics.
That's insane.
Yeah.
Which is why a heat pump dryer works, right? It's doing that same process. It's pulling the heat from out of the air. We're adding that heat, then heating the same tube up. We're able to heat that up, but we're able to then like work kind of like a dehumidifier and able to condense that water back out and have a drain instead of having as much air loss. So it makes the house, has the potential, depending on what brand, makes the house possibly more efficient. A high efficiency clothes dryer makes the house less efficient. Just a regular straight plain Jane electric dryer. A high efficiency dryer can make the house less efficient. How is that possible?
Casey?
I think it does in a lower runtime or longer runtime, don't it? Not that much heat.
A high efficiency dryer moves more air. So it doesn't need as much electricity because it doesn't have to heat the air up as much, but it's moving twice as much air, using more volume of air to dry the clothes more efficiently. So the efficiency of the appliance, like, sweet, we've solved this problem. But what happens to a house when you're moving more air out of a house, from in the house, out of a house, and then bringing more air from outside through the windows and cracks and doors back inside?
Yep.
Yeah,
Infiltration.
So it's psychrometrics, right? Now we have, where did the moisture from that air go? What else is it picking up through the walls and windows? And we're having to reheat it uncontrolled. And there's all this other stuff that goes in. So when people say, hey, I want to buy a high efficiency dryer, I'm like, whoa, 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 whoa. Let's make sure the house is efficient. Let's just get you a dryer.
Yeah. That was, talking about the same subject. I had this conversation with Bill Spohn from True Tech Tools, years ago. And we were talking about humidifiers. I'm like, well, I need a humidifier because I'm in Chicago and we get dry, and he's like, well, if you just fix your house, you're not going to need a humidifier.
Yes.
I'm like, wait, what? Because I didn't really put all these pieces together. And I started thinking about it. I'm like, well, that makes sense. Like, you're pulling in cold, dry air from outside and you're leaking out warm, humid air from inside. So it's not, if you have a nice tight house. I haven't had a humidifier now for 3 years. I sealed up my house, and with all the showers, the long showers that my teenagers take, I have an ERV in the house, and we're able to maintain humidity. I'm repurposing the hot, humid air from the showers. I'm using it to humidify my house.
So one of the things that I get so upset about seeing is the clothes dryer filter systems that people have inside the house. And so they're like, oh, I can reuse this heat. And it drives me bonkers for several reasons. One, if it's a gas appliance, yeah, you could literally unalive somebody. Bad, like horrible. And people have literally died from this. So the gas exhaust, it's a gas exhaust. You wouldn't run your car exhaust inside your house, so you wouldn't want to lose the heat. That's stupid. But people do that with the dryer. Now, move away from gas. We're talking about, well, what if it's electric? Okay, so cool. Electric, we're putting that heat back in the house, but you're also putting in a ton of humidity in the house. And that humidity is being dumped in one room. And so you got to make sure your paint is sealed where it's not going to have let the moisture soak into the wood and have mold behind the paint, or they're going to have mold in that room at all. And the people's like, oh, well, I live in Chicago and I have to have more heat. I'm like, or we could just fix your house, right? We could fix the house, seal the house up. You don't need all that moisture, and you don't need the moisture in one room. But also you end up with the fact of microplastics and all of the other toxins that's in your clothes. Soap itself, the fabric softener, all this stuff is horribly bad to breathe. So you put all this chemical in your clothes, and your clothes are made of all this polyester and stuff, and then you're tumbling it around, and all that plastic breaks down, and then you have all the softeners, and all this chemical soup is being dumped into the air. And that filter catches lint, but it's not going to catch all the other stuff, and then you're breathing it. Somebody in the HVAC grapevine posted they were concerned about flexible ductwork and microplastics. And I searched, I couldn't find anything about it. But I'm like, your clothes dryer is the biggest source of microplastics in your house. Ideally, get your washer and dryer out of the envelope of the house. Like, that solves a whole bunch of issues altogether. But again, not practical. People don't want to go into the garage. It's hot in the summer and cold in the winter. I get that, but if we're going to have that appliance, we need to think about the house as a whole. And if we dump those exhausts in and it's a gas furnace, you're going to kill somebody, or you're going to have humidity problems, or you're going to end up with microplastics in the house. So yeah, let's get the exhaust outside. And if we have humidity problems, let's not just dump more water in to overcome it. Let's fix the house, right? Let's solve the issue with the house. If I have a boat, I don't be looking at, man, what's the biggest bilge pump I could get? I need to get me a 350 horsepower high capacity bilge pump. Like, you know what else I could do? I could fix the leaks in the boat.
So let me ask you this on that. You were mentioning the exhaust. We're exhausting the microplastics in that. What about a heat pump dryer? What happens with that?
So they don't get as hot. Now, heat pumps have changed a lot since the technology came out. And I'm not recommending getting a heat pump dryer because there's still a lot of issues with them. The cost is high, repairs are high. But the idea is you're not getting as hot, so you're not having as much microplastics breaking down. Don't use fabric softener. I know that's a hard sell. I convinced my wife to stop using air fresheners and smell good stuff and candles. It took 3 years, right? So we've been married for 5, should know that. 2020, yes. So 6 years now. So yeah, it's a hard sell, but I got my wife to finally not be using things that contaminate the air inside the house just to make it smell good. But trying to convince Hayden let's not use fabric softener because it's it's all this poison stuff. You can then stop using the fabric softener. It's going to then try to condense a lot of that out, and it's going to condense that into the liquid form and try to drain that out. And you don't have nearly as much chemicals in the house. I mean, I think that heat pump clothes dryers are going to have a lot of answers. We just haven't got the technology and the affordability and longevity there yet. I would love to have one. And people may disagree, and that's okay. If you have one and you love it, let me know. Like, I want to know about it. And if you've had one and you hated it, I hear this a lot, but I also continue to tell me about it. It's just kind of that balance between, hey, this is a really great idea. Is it going to be cost effective for what I need overall?
Makes sense. And I know
It's like
Casey.
the U.S. Mint. Makes
Well,
sense.
they stopped it recently, right? At least the
Oh,
penny.
only the penny. No more
Yeah.
thoughts. You can't buy thoughts anymore.
Yeah, that's kind of sad. Makes me a little sad. But those pennies, if you look at the new pennies, they're like basically weightless, and they're nothing like they used to be, right?
Oh, really?
I don't know. Anyway, Casey, I was gonna ask you. I know you teach a lot of the CO class for NCI, and my big thing. I know a lot of people want to get away from. They want to go all electric in general. They want to go green. Everyone's got a different reason for it. I guess it's appealing to me, but one of the biggest things is safety. Like I don't know what your thoughts are on these, like the heat pump dryer, heat pump water heater, and that. But like, I mean,
Don't just because you get rid of a gas fired appliance doesn't mean you still can't be exposed to something.
that's true.
I mean, outside sources, barbecues, generators, pool equipment, whatever it may be. Just because you clear the house out doesn't mean that it's still not going to end up in there. And even electric ovens, you put those things in the cleaning mode, and if there's any debris or anything in those ovens, they'll off gas, and they'll create some sort of exposure. So I mean, they're great. I mean, I got a full electric house.
It's
I
electric.
I would, yeah, I'd like to go a couple of units to put back to gas, but I don't have that option. Um,
So you actually prefer gas?
yeah,
All right, interesting.
I like cooking with gas. I got a heat pump water heater. Doesn't bother me. I don't have no problem with that. I wish I had a gas furnace, for the winter time. But yeah, a couple appliances I wouldn't mind switching over.
I'm curious, like for both of you, how much experience you have with that? Like, how old is that heat pump water heater? Because I like be honest, I would love to have one. I want to install one in my house, but like I don't know enough about it. I've heard good and bad things.
2 years, I think I've had this one installed, and it was kind of a freebie. Somebody or a distributor wanted to see if they wanted to start selling them, and you know, asked if I'd be the guinea pig, so I did. And I don't mind it at all. Wintertime, because it's in the closet in my office. Wintertime it sucks because it gets really cold in here. I don't have it piped, or I'm not bringing outside air and dumping that air back outside. But summertime, I love it
Hmm.
because I have extra cooling capacity in my office. So it's it's pretty nice in that essence. And then I think I've seen about a 7 to 9% savings in utilities. Nothing huge, so it's not too bad. I don't know about
Interesting.
Ty.
So
Hmm?
I am not for or against either one, because when I talk about gas furnaces, I get the electrification people just super mad at me, and I talk about electrification, I get the gas heat people mad at me. For me, there's multiple things. For example, some houses you don't have natural gas available in your entire neighborhood, and getting propane can be a big expense. Having a tank
Hmm.
brought out, and then propane can be more expensive than natural gas. So it can be a big cost. And then the programs, keeping it filled, available. I mean, there's a lot of factors going in. So I'm never on like one team or the other. If I have a customer that already has an all electric house, hey, I have solutions that can make your house better. If somebody wants to go all electric, I have solutions to get you there. If somebody's like, hey, I got this gas furnace, I want this out of my house, cool, we're gonna get you there and get you there safely. Just like Casey said recently, there was a family that got carbon dioxide poisoning because their neighbor was running a generator near their house. And
Yeah.
so they didn't do anything wrong, but the CO came in. I see water heaters installed wrong all the my biggest thing for loving heat pump water heaters is because if you don't install it right, it won't work right. If you install a gas water heater wrong, a DIY especially, somebody is going to die. A lot of people die from water heaters more than anything else. So there's always a risk. But when it comes to DIY, I would much rather somebody DIY a heat pump than
Yeah.
DIY an actual gas water heater. And I've seen professionals, quote unquote, licensed people install gas water heaters horribly. Recently, there was a name brand hardware store that had their subcontractor go and install a water heater, gas water heater. They used a flexible pipe. I don't know what it looked like, single wall. It could have been double wall, but they looped it around. They did a loop de loop on it, and it made
Yeah.
a trap, and it poisoned the people. And so I love a gas water heater. I mean, it heats fast. They're awesome. At the same, I mean, have one in a camper. I have a tankless water heater for the
Hmm.
camper that's gas, and I also have a tanked water heater that's gas. We have a sprayer that we put on a stove and we can heat it up as backup. But here at the house, I have electric water heater. I would like to have a heat pump water heater, but our house is less than 500 square foot. Where the water heater is in the closet is right into the bedroom, no door. If I put that water heater in, it'll be nice in the summertime, but in the wintertime, we're going to be extremely chill, and also the sound of that heat pump being right there next to the bedroom. So for me, I would love to have it. I think as technology goes and time goes, we're going to have more options for remote condensers. And I think if we think of like a little heat pump condensing unit mounted outside and have the lines where it's easy to do, I think that will be the solution. It's going to be a little while before we get there, but I see that that's a big option. And it's just a matter of time. Like there's that Sandin pump that had really good ideas using CO2, but then there were some other problems like, oh, if you lose power, there's nothing to make sure that you keep the lines from freezing and cracking the CO2. Like there's never a like, hey, this solves all problems. There's
No.
there's never going to be that. But we think that there's many different solutions for many different people. And if we go in looking at, hey, what problems does the customer have and what are their needs, and then how can I solve them and help them get closer to their goals? That's what we look at. So if somebody is like, hey, I believe in saving the earth and going all electric and whatever, cool. My whole feelings is irrelevant. For that, against that, neutral, it doesn't matter. I want to help them reach their goals. If they're like, hey, I want a gas furnace and I make a ton of money on heat pumps and heat pump specialists, they want a gas furnace, I'm either going to tell them to go to somebody that can do gas furnaces, or me, who I love gas furnaces and know how to do it safely. I will go in and solve that problem for you and put you in. The gas system is going to be safe, and you will have a low-level CO monitor in your house on every floor to make sure you maintain that safety. So it's about, solving problems. What is your needs? Hey, I just have this electric house. I'm stuck with all electric. Hey, have you considered a backup generator? You're not against gas, but you want to make sure you're protected in the wintertime? Cool. Have you thought about a backup generator? I haven't thought about that. So something you can do. I don't do that, and I don't, but I know somebody who can. Here's a solution for you. So it's about solving problems for me. I'm neither in any camp.
You just hit on something that I've been running with for years. We as an industry, a lot of times stick to whatever codes and standards or what the big thing for the industry is now, and they follow that to a T. But a lot of other industries, even outside of kind of what we do, a lot of them, they build custom. They specialize in customizing something for their consumer, for their customer. And I think us as an industry and our guys out there, that we have to build a custom product for our customer. Whatever they want, whatever they need, that is what we do, as long as it's within reason, right? We're not putting in a 5-ton on, a house that needs only 3 tons.
Hold my beer.
Not to say I haven't done it, but different circumstances, right? But really trying to achieve what the customers want, not what a piece of paper or a book naturally says. I don't know. That's my 2 cents.
No.
And there is some limits to that. For example, I've had customers, they wanted a 5-ton unit. And so sometimes we have to find out, hey, why do you want that 5-ton unit? Why do you want that? Well, in the summertime, the house gets hot and I get uncomfortable and I want to be comfortable. It's like, okay, then can we agree to address that issue? Yeah, but I want to make sure I'm comfortable. Okay, if I address the issue of you being comfortable, is that fair? And they'll be like, okay, yes, that's fair. And then now I used to do this in the old days with psychrometric charts and numbers. It's way easier now with MeasureQuick, because I can go and show them what your system is doing right now. You have a 3-ton unit right now. That's what it's doing. You're spending electricity of a 4-ton, but you're only getting the capacity of a 3-ton. What I want to do is put you in a 3-ton that's going to get the actual capacity of a 3-ton system. It's what your house needs. And you're going to control the humidity. You wanted a temperature number, but let's monitor your house for a few weeks and see what your humidity is and what your temperature is, and see how those numbers change. And then they're now open to some other ideas and say, look, if you want to put a 5-ton unit in, here's what we're looking at. We're going to have to replace all of your ductwork, because your ductwork right now can only handle a 3-ton. That's it. So if you want this 5-ton, we're going to have to redo all of your ductwork. Here's the options for ductwork. We got flexible duct, we have metal duct, here's our options, but we're going to have to increase all of it. And then you're looking at a big unit. I cannot control your humidity. So you're also going to need a dehumidifier that's this big, that's going to be using that much power to keep your humidity under control, because your furnace is going to be your unit's going to be cycling on and off a lot. Then if it's going to be cycling on and off a lot, we're going to have to put in there's a control, I forget the name of it, that keeps the compressor from short cycling so that it doesn't kill the compressor. Yeah. We're going to have to do all these extra steps. It's going to take all this extra cost to make sure that we can get this 5-ton unit to work like you want it to actually work. Or we can put in this 3-ton unit. It'll work with your existing ductwork. Ideally, I would still love to upgrade your ductwork, but your ductwork can handle this 3-ton. The unit's already doing what a 3-ton would do anyways, and it's larger. Does that sound fair? Yes. Okay, now if I can keep your house in these parameters in summer, and then when it's the mid of summer, you're going to lose 3 degrees in the middle of summer, but in the off season, I keep it. Here's the parameters. If I can keep your house in these parameters, will you be satisfied? And they'll say yes or no or whatever, but it comes down to yes or no. Okay, now we've defined what the parameters are. So when summertime comes, and like, oh, they can complain about not feeling good, but look, we're in the parameters we agreed on. Your humidity's good, your temperature's good. Now it's above design conditions. We agreed that you would lose 3 degrees. We're still in those parameters. And it solves a lot of that problem later. And I know we all want to sell. We want that sell. We're up. A lot of the private equity is pushing for sales. But I don't try to compete with Walmart on sales. I try to compete with, hey, I have unique custom work that I can do. I can solve problems for you. You look at home builders, you got the ones that just do mass production as fast as they can possibly build it. You can look online about the home inspectors, and you see the problems they're not solving. Or you can be like, hey, I want a well-built home. So you go to somebody that can do that. And for me, hey, let's solve custom problems. You come to me, let's solve some problems. But we need to set some parameters, because just feeling good isn't enough. We have to, set some benchmarks here.
Yep, exactly.
The interesting point behind what you're saying is about the temperature and the parameters in that. I think a lot of homeowners get caught up on that number on their thermostat. They walk by their thermostat and they see the number is not what they set it to, and they lose it. And they're like, it's not working. This is terrible. And they just get very upset by that. And it's like, put a piece of tape over the number that's displayed on the screen of your thermostat. How do you feel? Do you feel good right now? Because it might be a couple degrees warmer, but you have lower relative humidity than what you would have otherwise, right?
And even that can be catchy, because we go for walks every night together. It's a way for me to just, we leave the phones behind. We just go and just unwind, family time. And when we come back, it's like, oh, the house feels hot. We sit down, it's like, oh, the house feels hot. And I'm like, I have to remind myself, who knows this stuff. It's like, no, the house hasn't changed in temperature. The temperature outside was much, much lower. So it's a lower temperature that my body acclimated to. And then I was also burning some energy. So my body's running at a higher temperature. So it's kind of that balance between also not only how you feel, but also the conditions. One of the schools I worked at, the dean of the school was so mad because her office wasn't cooling right. And it cooled great all summer, middle of summer, cooled good. And the humidity was good. The temperature was good. But then when the fall came, she started complaining that her office was too hot. The difference was the outdoor temperature lowered, and she got acclimated to these cooler temperatures. So then she would go into her office, which was the same temperature, same humidity she's always had it at, and she was complaining that it was hot because she's used to walking in her office and she's used to feeling the cool air. But now when she walked in, the outside temperature is lower and it didn't feel cooler. So what does she do? She's blamed it on us. Like, hey, my office isn't cooling as good. No, the office was the exact temperature it should be. Did we lose Casey?
That is interesting. Yeah, I think we lost them temporarily, but we should be wrapping it up anyways. But my thought on that, it's funny because I feel like in my house, myself and my wife are constantly battling over the thermostat, because either I'm sitting at a computer working, not moving in the wintertime, and I'm like feeling kind of cold, you know what I mean? And I bump up the thermostat, and then she's running around the house cleaning and that, and then she feels warm. So she turns down the thermostat. So, I mean, when you say, what does the temperature feel like? It's your feelings, and it's an opinion. It's a personal thing, and your opinion can change from time to time. So
yes, and this is why fans are important. I wish there was a way on the thermostat to be like, hey, before you drop this down and cool the entire house down a few degrees because you're temporarily warm, maybe we suggest turning on a fan, and a fan makes all the difference in the world. In Las Vegas, it was like, it would be pretty warm, and I usually kept my house about 85 or so. People were like, 85? With a fan on and the low humidity and me staying hydrated, the evaporation off my skin, I would stay comfortable and didn't have to spend money on the electric bill. Talking about the feelings, I was working in New York, and we had a walk-in cooler that we fixed, 40 degrees. Everything was working perfectly, and the thermometer on the wall was broken. And I suggested that we replace it. They didn't want to replace it. Okay, no problem. And then that night, I get a call in the middle of the night. They had a late dinner thing. They had a party going on, and the guy's freaking out because the walk-in cooler is not cooling. Man, so we jump in the truck, we go back there. I'm like going over every possible thing it could be, working my mind over every scenario, stressing out. And I get there, put the thermometer inside, perfect 40 degrees. Perfect 40 degrees. What was the problem?
The thermostat registered a different temperature than what was actual, or
It wasn't registering anything at all. He's used to walking in, and it feels cold, but it was like 0 degrees or something outside. And so when you walked through the snow to where this cooler was, and you walked in, it was warmer, 40 degrees. It was still pretty warmer, but because he didn't have a number to go on, it was false. And with air conditioning, we shouldn't just go off of a number. It should also be humidity as well, or maybe even if it's one number dew point. But number, we need a range to kind of go in, and then also we need to acknowledge the moisture in the air, whether it's dew point or humidity. We need some way of putting that into the parameters.
well, there it goes. On that note, it's probably a good time to call it. We've been going for over an hour now, but this has been a good conversation. I know we kind of jumped all over the place. Just the other day, want to finish it with this. I was rereading for the second time Psychrometrics Without Tears, and I got to tell you, I was like kind of crying a little bit while reading it. Because it's still like, even though it's like I think it's supposed to be dumbed down, there's still a lot to know and to learn. So you got to like pace yourself as with anything learning, right? So Ty, I've learned a lot from you today, like I always do. You said you want to have a lot of fans in your house so you could cool yourself. You're already a pretty cool dude, though, you know? So, yeah, on that note, anyway. But I'm bummed. So thank you. Any closing thoughts, either one of you?
I have
Oh,
one.
this is great. Sorry, Ty, go ahead.
Go through some of the old books like that. Like I have the review of Vacuum for the Service Engineer, and I go through that again, and I still pick up stuff that I didn't pick up the first few times. Like you talk about Psychrometrics Without Tears, you can go through those again, and you get new stuff out of them. Like it's like taking a class again you've already taken. You will always get something new out of that because you can't remember everything that's in that book or everything in that class. So when you go back through some of the fundamentals, it's important that we revisit that because it can be so far gone that we forget because we're not using it in the everyday. But those are the fundamentals that what makes everything happen around us, the science behind us. And don't be afraid to keep learning something new. We have a little private group chat, and I get to ask questions, and other people ask questions, and we just work ideas between us, and it just gets you thinking, and it gets you thinking outside of the standard everyday stuff because we kind of get robotics.
Mm-hmm.
We go and change a capacitor, we're heroes. We change a contactor, we're the heroes. And then you get to when it's actually a problem of, hey, my house isn't comfortable and I got a new unit. Oh man. And that's where those fundamentals are coming in. And that's what makes it fun though. Like I'm one of the obsessed people. I don't care if we did DIY stuff. If the homeowner changed capacitors and contactors, it's going to be more work for me anyways. But I would like that because now I'm going and solving problems instead of just changing parts. And I think our job is a lot more fulfilling when we're able to really solve problems. Something that you can't just get off of the internet. Something you can't just ask AI, hey, my house is uncomfortable, what do I do? Like somebody, a professional has to go in and evaluate the house. It's like the Matrix. You see the numbers, and once you see the numbers, know how a house works, then you can manipulate it. The air, once you see how the air works. Willis Carrier did this. He mapped the air with the psychrometric chart. He saw all the numbers like in the Matrix, and he was able to like, and then he's able to dehumidify it and control the temperature and humidity. And he didn't even use refrigerant in his first design. There's many ways to solve it, but once you see the numbers and see how it solves, and you see those basic physics and fundamentals, man, you're unlimited in what you can do. And it feels good when you're able to solve problems that nobody else can do.
Blowing me away. That was a mic drop. How about you, Casey?
Yep.
Any final word?
I got to agree. I mean, that's the day that I started learning the invisible stuff is the day I actually turned this into a career, and it actually was fun. Because I mean, some of the guys out there know I was 1 foot out the door. I'm like, HVAC is stupid and boring. Well, when you work in new construction, it is. But when you can take tools, discover invisible things, stuff moving all around, and just different science and math and all those fun things going around, I mean, it really changes everything, and it becomes enjoyable and fun. I mean, being able to be a investigator or a detective in air and psychrometrics and all that other stuff, it's just it turns it into worthwhile, you know. So
For some of us, it's a job, but for Willis, he turned it into a carrier.
oh man.
All right, guys. Thank you guys both. It's been awesome as usual. Great talking to you, and we'll see you in the next one.
Oh, you know it. Thanks, Ty.